we got a really fun section, in my opinion, today, which is the numerical integration. Um, you know, the reason I always find this section interesting is, life is not made up of continuous functions. And so to be able to model things in real life, we use a lot of what are called numerical methods, which is basically what you're seeing here. How do we deal with finding an integral of a function that doesn't have a nice, clean antiderivative? And that's where numerical integration comes in. And in the bigger scheme of things, numerical mathematics is a way of approximating things using numerical methods to help us deal with the fact that life isn't made up of nice, easy, continuous functions. We build all our theorems on the nice continuous functions, and when we have them, it's great. But when we don't, we have numerical mathematics. So what I'd like to do today is I'd like to go through an example of all the rules that you saw in the lesson, so you can see how the formulas translate for a given problem. And then I'm going to let you guys try one. And then we're going to come back together and talk about error estimation and look at an example there. And then by the end of class today, you'll be ready to start your first take-home problem. So I'll spend the last few minutes of class talking about that as well. All right. As always, I'm going to record today's lecture. So anything we go over will be recorded. If questions come up while we go through these, feel free to put them in chat or turn your mic on and let me know. All right, so here's the goal, is to calculate the integral of x e to the x dx from 0 to 1. Now, this is one we can do by hand. I'm picking it for a very specific reason, so I want to show you some connections. The ones I'm going to give you in the worksheet later, they won't be able to be done by hand. So, well, they can be done by hand with a numerical approximation, but we can't find the antiderivative. It's a fundamental theorem like we. All right, so we want to calculate the integral with 6 intervals, and I'm picking 6 specifically because I want it to be even, because we're going to do all 5 methods. For Simpson's rule, we do need n to be even. And what I'm going to do is I'm going to call the integrand x e to the x, little f of x, and here's its graph. So here's the formula, f of t, delta t, f of t1, delta t. So we're going to do the left-hand rule first. That t0 means we start at the leftmost endpoint. So we're going from 0 to 1. And then we have to break this up into 6 intervals. Well, right now it's only broken up into 5. So I need to find out what the width of each interval is going to be if I break it up into 6. So I have to calculate my delta x or my delta t. Well, it's the length of the interval, 1 minus 0 over n. That's always going to be the case. Okay, right here. So it's 1/6. So each interval is going to be broken up into 1/6. So I'm going to put those on the graph. So I have 1/6. I'm going to leave it in terms of 6, but we might in practice reduce these. 2/6, 3/6, which would reduce to a half. 4/6, and finally 5/6. And like I said, we could reduce 2/6. That's 1/3. So let's write it up here because we need some room later. 1/2 and 2/3. Okay. There we have 1, 2, 3, 4, 5, 6 intervals. Now let's talk about left-hand rule. So we're doing left-hand rule with 6 intervals, which is right there. Now the big thing about the left-hand rule is it starts at the leftmost endpoint. It starts at 0, we end at 1. And one thing I want to notice that every term gets multiplied by the delta t or the delta x. We're just going to save that for the n. So what I'm going to do is I'm going to start at f of 0, and I'm going to use f instead of the function, but I'll show you how that works out here in a second. Then we have our next point is 1/6 plus f of 2/6 or 1/3. It doesn't matter. You're going to get the same answer either way. F of 3/6 or 1/2 comes next. F of 2/3. And finally, f of 5/6. And I do need to multiply this whole thing, brackets to make it a little more obvious, by our delta x, which is 1/6. So what's going to happen, and I'll do it for this one, but I won't do it for the others just because of time's sake. I don't want to bore you. What's going to happen is I'm plugging these values into my integrand, which I just decided to call f for notational purposes. So what would that look like? Well, 1/6, 0 times e to the 0, plus 1/6, e to the 1/6, plus 1/3, e to the 1/3, plus 1/2, e to the 1/2, plus 2/3, e to the 2/3, plus 5/6 times e to the 5/6. Okay. A couple things I want to point out. Number one, all I'm doing once I have my intervals broken up is all I'm doing is plugging those numbers into the integrand to get those function values, which would be along this blue curve. Okay, again, we're going from 0 to 1. Now, the other thing, I used 0, but I didn't use 1. That's because this is the left-hand rule, so the rectangles are being made with the leftmost endpoint. So let's think about what that would look like. Well, a rectangle with the leftmost endpoint would look like this. So I'm using 5/6 to calculate the height of the rectangle. I don't need to use 1 as well. I've already calculated it. The other thing you can do is this is supposed to be 6 intervals. I have 1, 2, 3, 4, 5, 6 rectangle heights. If I did f of 1 on there, it would be 7 and it'd be too many. All right. So left-hand rule starts at the leftmost and ends 1 short of the right. Let's change that back to purple. Now, I've already calculated these because we don't need to go through that part. You throw this in. This is something you put into your calculator all at once. Don't do it piece by piece and try and add it up. You're going to run into round off error. We want to be accurate. This comes out to 0.7873738. Okay. Now the left-hand rule and right-hand rule you've most likely seen before, probably in Calc 1. Right-hand rule looks almost exactly like left-hand rule. It has the same delta x. Let's scroll to the rule. Here's the only difference. It starts at t sub 1 and ends at t sub n, meaning we're going to start at the very first. This is our t sub 1. This is our t sub 0. We're going to start here and end at 1. So we're basically shifting it to the right one, but everything else is the same. So we're going to have f of 1/6 plus f of 1/3 plus f of 1/2 plus f of 2/3 plus f of 5/6. Oops, and I'm short 1. Look, 1, 2, 3, 4, 5, but I'm supposed to have n equals 6. So I know I have an error in there. I need to go all the way up to f of 1. You'll put those into your function, into your calculator. You should get 1.236785. Notice this one came out lower. This one came out higher. Well, let's look at what a right rectangle would look like. This is the easiest one to show it on. We do the right point and go across. Notice how the green rectangle gives us an overestimate. red rectangle gives us an underestimate. If we have an increasing function, that will always be true of our right and left hand rule. Decreasing function, that flips. So we're perfectly, this we know is an underestimate, this we know is an overestimate of the actual integral. Averaging them would give us a much more accurate answer. Well, it turns out they're actually already averaged by the trapezoid rule. So let's go to the trapezoid rule, then we'll come back to the midpoint rule. I want you to see how this formula works. So one way to do the trapezoid rule is to average these two, and we will do that here in a second. But the trapezoid rule, it uses the same delta x, uses all, these are all the same values. So what we're going to have is 1/6 divided by 2, and then there's a pattern. 1 times the leftmost endpoint. Remember, the leftmost endpoint is 0. F of 0. And then all the middle ones get doubled. 2 times f of 1/3 plus 2 times f of 1/2 plus 2 times f of 2/3 plus 2 times f of 5/6. And then now this is the rightmost endpoint, so it only gets counted once. So f of 1. Now, a couple things I want to point out. This does use all 7 values. The reason is because it's basically adding the right and left hand together, and then this dividing by 2 is taking their average. So we're going to get the average of the right and left hand rule, which is an other way of calculating the trapezoid rule. I just want to show you this way. But if you already have the left hand and right hand, you can just add those together and divide them by 2. You're going to get the same thing. And for the trapezoid rule, you get, you get 1.01, 0261, 394. All right. And again, that's going to be the average of these two numbers. Now, I didn't go to quite as many decimals, so that the end might not be quite as correct. But this one I calculated very accurately because there's something we're going to look at here in a little bit. All right. So those are 3 of our rules. I want to just pause there for a sec to give you guys a chance if you have any questions so far. Again, same thing. I'm not doing this step for the right hand and trapezoid rules just because all I'm doing is plug in 0 for my integrand 1/3, write it all out, and calculate it all at once. I'll never ask you to calculate more than 4 to 6 intervals by hand. Anything higher than that, we'll use technology, and I'll show you that in a little bit. Okay. Midpoint rule. Yeah, those are the 1/6 right here for the trapezoid rule. And that comes, if we look at our rule here, that's from this delta x. It's the same delta x from the left and the right hand. They all have, this delta x, delta t, whichever we're calling it, it's the same for all the rules. So once I've calculated it, I'm going to be using it in every rule. Other questions? All right, let's look at the midpoint rule. The midpoint rule is the one that's a little bit different. It does use the same delta t, which is the same as our delta x. So it's going to use this. It's going to be the same for all of them. There's going to be one thing that's going to be different. So I'm already going to start with the 1/6 out front. Here's the difference. What I'm going to be putting in for my function, these f ofs, is going to be the midpoint of each interval. So there will be 6 of them. 2, 3, 4, 5, and 6. And I'm doing this way just because I want you to see something and I want it to be obvious when you go back to look at these. What we need is to calculate the midpoint of each interval. How do you do that? You just average these. So 0 plus 1/6 divided by 2, and that's going to give us 1/12. Okay, so the midpoint, which will lie right in the middle of those two, is 1/12. All right, now remember our delta x is 1/6, which is the same as 2/12. So basically now I'm going 2/12 to the right each time. So the next one here is going to be 3/12. Then I go another 2/6 and I get 5/12. Another 2/6 and I get 7/12. Another 2/12, excuse me, and I get 9/12. These can obviously, some of these can be reduced. And another 2 and I get 11/12. If you want to reduce these down to 1/4 and 3/4, that's totally fine. But those are going to be 1, 2, 3, 4, 5, 6, the numbers, 12 there, that go into these parentheses here that I left open. Okay, so 1/12, 3/12, 5/12, 7/12, 9/12, and 11/12. So those are going to be the inputs into our F, into our integrand. Calculating that, the midpoint rule gives 0.99487,246. All right. There's our midpoint rule. Here's the thing, and the midpoint rule does take a little bit longer because not only do we have to find the endpoints of our intervals, we have to find the midpoints. And I'm going to show you something interesting about comparing which rules are best and worst. So Simpson's rule is the last one we're going to do. And, you know, when I break you into groups, you guys are going to get a chance to try all of these. All right, Simpson's rule. All right, notice it's delta x over 3 out front. It's the same delta x, 1/6 divided by 3. That goes out front. Notice it's the same pattern. It's not the same pattern. It's a similar pattern to what we had on trapezoid, except it goes 1, 4, 2, 4, 2, and it keeps going 4, 2, 4, 2, 4, 2, 4, 2, and then 4, and then back to 1. And that's why we need n to be even for this pattern to work. It's going to go back to using the purple numbers, and it's going to use all of them. It's going to use from 0 all the way to 1. So f of 0 plus 4 times f of 1/6 plus 2 times f of 2/6. Let's just write them in 6. That might be easier. Plus 4 times f of 3/6. And then we go back to a 2 times f of 4/6. Then back to a 4, f of 5/6. And then finally, our last one is just times 1 times f of 1. And there is Simpson's rule. And that's how you translate these rules into what we're doing on here. And this guy is approximately 1.000 and one more 0, 3359. All right. Now, all of these methods are estimations. Left hand and right hand are okay. Trapezoid is better because it averages those two. Midpoint is about as accurate as trapezoid. Simpson's rule is the most accurate. All right, well, we're going to prove that by looking at the errors. When you guys are asked for errors, what you're being asked to do is measure the difference between the estimated, which are the ones we found. We're only going to do this for trapezoid, midpoint, Simpsons. Don't worry about left and right. We're going to find the errors in these, which is the estimated minus the actual. We take the absolute value. Well, like I said, this is one we could do. This interval is 1. So basically, if I want the error in the trapezoid rule, I'm going to take my value for the absolute value of my estimated for the trapezoid rule, this number here, and subtract 1. And we use absolute value because we always let errors be positive. We don't worry about them being negative. This comes out to 0.0102, basically all those decimal points there, 39. All right, we can do the error in the midpoint rule, which is going to be the absolute value of our midpoint rule with 6 minus 1. And this comes out to be 0.00512754. And finally, the error in our Simpsons is going to be our Simpsons with 6 intervals minus 1. And again, it's just basically going to be those leftover decimals. 0.00003359. All right. Now, here's what I want to show you. And this is pretty cool. Notice which one had the smallest error by far. Simpson's rule had the smallest error. That verifies that Simpson rule is most accurate. And look at this. 1, 2, 3, 4 zeros before we even get to a number. There was only 1 0 on trapezoid rule and only 2 zeros on midpoint rule. That's not a coincidence. Well, we're going to look at the error estimates in these and find that Simpson's rule is 4th order accurate, which is why we're getting so many more zeros in the error. It's so much small. It's always going to be a much smaller error than trapezoid midpoint. Another interesting thing that's always going to happen. Notice the error in the trapezoid rule is 0.01, and the error in the midpoint rule is 0.005. So the error in the midpoint rule is approximately 1/2 the error in the trapezoid rule. Again, not a coincidence. That always ends up happening. So midpoint rule is a little bit more accurate than trapezoid rule, but it's more work because we have to find the midpoint of each interval. It's more work by hand, it's more work to code. The Simpsons rule, though, is significantly more accurate than trapezoid or midpoint. And really, it's almost as easy as doing trapezoid, except notice we had those 4s in there where trapezoid was all 2s. Okay? And that's why n has to be even in order to do Simpson's rule. Simpson's rule, because we're guaranteed to get the most accurate answer, and it's really not that much more work, either by hand or via computer. But the issue is we need n to be even. If n's not even, we can't use Simpsons. So, like you said, probably next best is to use trapezoid because it's not that much less accurate than midpoint, but it's a lot less by hand. So, in practice, that's basically what I would do. Now, in the homework, you might get a problem that tells you or asks you to use a specific method. That's a little bit different. But as mathematicians trying to get the best answer, that would be our approach. Other questions? Okay, a couple things I want to show you. Number one, there's a whole bunch of numerical integrators out there that you guys have access to on the web. This is one. I think it's linked. It should be linked in the lesson. You know, we're going 0. Show you how it works. To 1. I'm using n equals 6. This does not have midpoints. That's because midpoint's a little bit tougher to code. But I can do the left sum. There's my answer. Right sum, trapezoid, and Simpsons. All the answers we got. If we wanted more decimal places, we can get that too. All right, so let me throw that up. I'm going to go through some PowerPoint slides here. The link was in today's invitation, but in case you didn't get it, here it is, in case you want to follow along. So one of the things, and this is true of all numerical mathematics, because we're estimating, we're always interested in how good our estimation is. Now, earlier, actually, let's go back to our work from earlier. I calculated the errors at the bottom here. Well, I could calculate the errors because I knew the actual value. Well, if we know the actual value, we don't really need to estimate the actual value. So what we need to be able to do is estimate the error in our estimation so we know how much we're off by. So what we're going to do is look at error approximations for Simpson's, trapezoid, and midpoint rule. And then we're going to calculate we're going to do a couple problems with it. So let's make that a little bigger. Again, I put the slides in chat, so if you want to follow along, feel free. There's not a lot of slides, just a couple. All right, so let's talk about what this says. So first 2 are for the trapezoid, hence the T, and the midpoint. So this says if we can bound the absolute value of the second derivative of our integrand. So again, you know, this, if we're looking at this one, this is our f of x. We want to try and bound the second derivative of this guy under some k within our limits between 0 and 1. Then the error of the trapezoid rule is guaranteed to be less than that value k times b minus a to the third over 12n squared. The error of the midpoint rule is less than or equal to k times b minus a cubed over 24n squared. Remember what we talked about earlier when we compared those two errors. Let's change colors here. Right, we had our trapezoid error, which was right here, and our midpoint, which was right here. And we noticed the midpoint was a half of the trapezoid. Well, look at this. This one gets divided by 12. This one gets divided by 24. Everything else is the same. So the error estimate for the midpoint rule is exactly half the error estimate for the trapezoid rule. So if you found the error estimate for the trapezoid rule, all you got to do is divide it by 2, and you've got the error bound for the midpoint. What these are the maximum possible error. So that allows us to know what size n we need in order to get as accurate as we are desired. Simpson's rule is very similar, but finding the k is a little bit different, and the formula is a little bit different. For k, we want to bound the fourth derivative, and it's the absolute value. So we want to bound the magnitude, not necessarily the maximum. We want to look at the max and the min, whichever has larger magnitude, that's our k. And then the error of the Simpsons rule is k times b minus a, this times to the fifth over 180 n to the fourth. Remember those extra zeros we talked about earlier? That's what these exponents are making happen basically in the error estimate. It's 2 degrees of order accuracy more than the midpoint in the trapezoid. Now, I don't want to worry about degree of accuracy or anything like that. We're not going to get that specific in this class, but we want to recognize that, hey, look at these higher exponents. Simpson's rule is significantly more accurate than trapezoid or midpoint. All right. Now let's talk about how we use these formulas, okay? And depending on time, we'll definitely do midpoint rule. Maybe we'll do trapezoid rule. All right, so how large does n have to be to get the error of the trapezoid rule with 0.0001 of the following definite interval? So same definite interval from before, 0 to 1, e to the x squared dx. Oops. And what we're going to do, I'm going to show you how to leverage technology to do this one. We want the error in the trapezoid rule to be less than or equal to 0.0001. That's what we want. Okay. Let's go back and talk about how we use this stuff. All right. Very first thing we should notice is we need k. We know e sub t, that's this guy. We know a and b, 0 and 1. N is what we're trying to find. So k is all we really need to be able to solve this. All right, so how do we find k? We have to optimize the second derivative. So remember the second derivative of what? Well, our function is our integrand. So we're basically letting f of x equal e to the x squared. Now, guys, there's nothing wrong with doing these derivatives by hand. I just want to show you how you can use technology, because you're going to have a similar problem for your take-home problem, and you are allowed to use technology. You guys have done derivatives by hand. Let's see how we can use, in this case, I'm going to use Wolfram Alpha. But you can use Symbolab, any of the other programs. One of the things I want to point out, and I just found this out about Wolfram Alpha, you can put things in natural language or in math input. So there's all your math symbols. I haven't played around with that enough yet, so I'm going to just show you how I would probably do this if I were working on this one. So second derivative of e to the x squared. And there's my second derivative. F double prime of x equals 2e to the x squared times 2x squared plus 1. And we want to optimize this on the interval from 0 to 1. It's a closed interval, and it's a bounded interval. So now we're back into Calc 1. We want to optimize this function on the interval from 0 to 1. It's probably been a little while since you've done this, so let's run through how we do that. First thing we do is we look for any critical points on our interval. Remember that critical points are zeros of the derivative of the function we're interested in. Again, this is the function we're interested in. Don't let these double primes throw you off. Call it G if you need to. But we're going to look for any critical points by finding the third derivative of the function we just found the second derivative of. Look how easy that is to do in Wolfram Alpha. So there's our third derivative. Now remember, why are we finding the third derivative? Because we need to see if there's any zeros in between 0 and 1, if there's any critical points. Okay. So solve, and we'll put in our the third derivative. And then times x, then times 2x squared. And guys, again, this can all be done by hand. You could use Symbolab. I just want to show you how you could do it with Wolfram Alpha, just one option. All right, there's our results. We have one at 0 and the other one is imaginary, so we don't need to worry about it. 0 is one of our endpoints, so we were going to check it anyways. Again, we want to optimize the second derivative. So to optimize on a closed bounded interval, we evaluate our second derivative at our endpoints and any critical points. If we don't have any critical points, we're not too worried about that. So putting in 0, we have 2e to the 0 2 times 0 squared plus 1. That's 3 times that 2. Let's see. Oh, excuse me. That's 0. So that's 1. E to the 0 is 1. 2 times 1 times 1 is 2. Now remember, we want the largest magnitude. So we don't care about positive or negative. We just care about the largest possible magnitude. We put in 1. 2 times e to the 1. 2 times 1 squared plus 1. This time we get 3 times 2. Did I forget the e? Ah, geez. Sorry, guys. Going too quick. Apologies. Hopefully I said e. 2 times e to the 1 times 2 times 1 squared plus 1. This is 3 times 2 is 6e. Again, if we had a positive, if one of these were negative, don't even worry about the negative. We're going to take the absolute value. So we could even do this. They came out positive anyways, but you might get one where they don't. 6e is much larger than 2. So that is our value for k. We can now set up this inequality right here for the trapezoid rule. So setting that up, we got 0. That's our e sub t. 1 is less than or equal to our k, which is 6e times 1 minus 0 to the third over 12n squared. Again, n squared is what we're trying to solve for. So this, we can solve this explicitly for n. So first we'll solve for n squared. We'll multiply both sides by n squared. Basically, cross multiplying. And that's going to do this, 6e. This one came out kind of nice, 1 cubed. I'm going to write it in there for notes purposes, and we'll put the 0.0001 down here. And then finally, to solve for n, we'll take the square root of both sides. And we will get n has to be less than or equal to, as a decimal, 116.58. Okay, you can throw this in your calculator, you can throw it in Wolfram. Now, n for trapezoid rule must be an integer. So we're going to round up to the next integer, and there is the number of intervals we would need to guarantee that our value from the trapezoid rule for this integral is within 0.0001 of the actual answer. It may be even closer than that. This is a conservative estimate because we want to be able to guarantee it. But that's what this does. That's what these error bounds do. They allow us to figure out, okay, what size n do I need to figure this out? Yeah. Before I go on, questions at this point? Okay, couple things I want to mention, and then we're going to do. We have enough time. I think we'll do Simpson's rule just for kicks. We'll do the same error bound. Let's do it for Simpson's rule. Number one, why are we doing this? Guys, today's computing technology is good enough that we don't necessarily need to worry about the size of n. There was a time where knowing the n ahead of time was really important, because whether n was 100 or n was 1,000, it was very expensive in computing time. People were either doing it by hand, or just computers were very slow, and you would actually see a difference. It might take 10 minutes to do n equals 100. It might take hours to do n equals 1,000. So knowing that n ahead of time was very important from a computational standpoint in the past. Today, it's not as important from a computational standpoint. But there is something theoretical that I want you to take away from this. And that is because numerical mathematics, those of you guys who go on in math, engineering, Even in computer science, we deal with a okay. I saw that, Taylor. Yeah. No, k is not going to be a function. K is going to be the maximum magnitude of a function. It's going to be the optimization of a function. So with numerical mathematics, error estimation is a very big part of it, because we need to know if we're estimating everything, we need to know how accurate our estimates are. So this is just giving you kind of a taste of how error estimation is done. Okay, we got some time. Let's do Simpson's rule. You know, why not? And all right. So we're going down to here, but I want you to see that it's not that different. All right, we're going to do. Let's change colors. Take a break from the purple. Same thing. 0 to 1 of e to the x squared dx. And we want to use Simpson's rule so that the error in Simpson's rule is less than or equal to 0.0001. So again, we're considering our f of x to be e to the x squared. And we're going to follow the same process, except now we're going to optimize the fourth derivative. All right, so fourth derivative. It already knew what I wanted. How nice. All right, it's a little bit longer. This would have taken a little bit longer to do by hand, but it's still very doable by hand for those of you guys who like to do these by hand. So 4e to the x squared, 4x to the fourth plus 12x squared plus 3. That's our fourth derivative. We have to optimize that. I'm going to show you another way of optimizing this guy. Again, we're on 0 to 1. We saw one way in the previous. What we would do is find the fifth derivative, see if there's any critical points between 0 and 1, and check 0, 1, and any critical points in our fourth derivative. That would be the exact same that we just did. I'm going to show you a different way. One thing I do want to mention, guys, like I told you, this would suffice as your work on the take-home problems. All you would do is get a screenshot of your entry into Wolfram Alpha and the output, and include that with your solution. Okay. So if I were doing this as part of my work, I would say, okay, well, I'm going to grab a screenshot right here. I'll paste that into my Word document. I'll type up my conclusions, or, you could put in handwriting, or, you guys can do a combination of them all. All that I ask is that it's neat and it's organized and it's orderly, and your final submission is as a single PDF. And we'll talk a little bit more about that once I finish this problem. Okay, but that suffices as work, guys, for the take-home problems. Totally. All right, another way of optimizing. Check this out. Maximize. We're going to put in our fourth derivative, 4e to the x squared. And again, like I said, you can use the math input. I'm just familiar with doing it this way. I haven't had so much practice with the math input, and it will work just fine. 4x to the fourth plus 12x squared plus 3. And you got to tell it where, on 0, 1. Now this will give me the maximum. So max F4 is at, so right here, it's telling me the max is 76E at 1. Now, here's the thing. Because I maximized, I do still have to check the minimum, because if the minimum is less than negative 76E, that's what I'm going to use for my K. Because remember, we're using the absolute value. So if you do it this way, remember to do the max and the min. Okay. All right, minimized at 0. So the min is at 0. We would have found that out had we done it the other way just fine. There is our K. So now we set up the error for Simpson's rule. So 0.0001 less than or equal to our k, which is 76e, times, once again, it'll just be 1 minus 0 to the fifth, this time over 180 n to the fourth. The solution will be very similar as the last one. N to the fourth has to be less than or equal to 76e. That thing comes out to be 1. I'm not going to put it in there this time. 7, make sure it looks like a 7, over 180 times 0.0001. And then we're going to take the fourth root of that. Okay. So n has to be less than or equal to, I'm going to just go ahead and use Wolfram alpha because I don't have this one calculated. I didn't know we had time for it. So 76e divided by 180 times 0.0001. And I'm just going to raise all of that to the 1/4 power. There we go. All right, so n has to be less than or equal to 10.35. Okay, we don't care about the rest. Like last time, we need this to be an integer, but now we're doing Simpson's rule. So it doesn't just have to be an integer. What did we say about Simpson's rule? What do we need n to be? It has to be an even integer. So if you try to do 11, it won't work. So we have to go to the next even integer, and our n would be 12. Now, here's something I do want to point out, just because we just did the other one.